Hi and welcome to Unit 2 Topic 3 Video 4, and in this video and the next two videos after this we're going to be looking at matrix multiplication. So how we multiply matrices, and I want to remind you very quickly that all of the arithmetic we've done so far, well, they're human constructs. We've designed those arithmetic to suit context and real life situations that we are in. So for example, we add two things together. I have 2 bananas, you have 3 bananas. We add them together. Between us we have 5 bananas. There's a reason why we add in the way we add. Subtraction works the same and multiplication works the same as well. So if we have 3 groups of 2 bananas, well, we know we do 3 times 2 will tell us we have 6 bananas in total. It saves us doing that repetitive addition. That's what multiplication does, saves on a repetitive addition. So you might think with a matrix that it's simple. We just multiply the first cell by the first cell in the second matrix, keep on going like that. But again, it's a human construct, and it turns out there's really no contexts that allow for that type of multiplication to be useful. So we have a different way of multiplying matrices. I'm going to explain that way to you now, and it does tend to look a little bit complex, and it's going to be pretty colourful, but it's very procedural. So we'll run through that in a second. So just remember this amazing map we had in the previous video, A, B, C, D. We assumed that they were towns of some sort, and there's road connections. It led to this matrix here, 0, 1, 1, 0, etc, etc. Now I want to know, how do we multiply matrices? What does R times R mean? What about R squared, R cubed, and R squared? So let's go back up to this matrix. If I multiplied it together the way we might expect, we'd probably get something like R squared is equal to 0 times 0, 1 times 1, 1 times 1, 0 times 0, 1, 0, 0, 1, 1, 0, 0, 4, there's the first interesting one, 0, 1, 4, 0. And what does that mean with respect to this graph, with this model, this road system? Well, not much really. I'll tell you what R squared actually equals, and I'm going to show you where this comes from a little bit later, and you could always come back to this part of the video and do the R squared yourself, would be a good idea. So R squared actually, if we do the calculation, it's equal to 2, it's going to take me a minute here, 0, 0, 3, and then this one is 0, 2, 3, 0, and then we get 0, 3, 5, 0, and then we get 3, 0, 0, 5. Okay, that would be it there. So that took me a little bit longer than maybe you should have, but multiplication for matrices is actually a bit tricky in terms of the time it takes to do it. Now, here's the interesting thing here. If I look at this 2, it's a relationship between A and A. And in the road system, it actually represents how many ways there are of getting from A to A using 2 roads. Now, that you might be looking at this going, well, there's no ways. Well, actually, what this is counting is I can go from A to C, and then from C back to A. So 2 journeys are made. I go through one town, and I get back to A. Or I can go from A to B, along that curvy road, and then back to A. So that works. Now, there's no ways of getting from A to B, or indeed B to A, so that's this 0 and this 0. There's no ways of getting from A to B or B to A using just 2 passes, because B goes to A or D, but then I can't get from D to A or A to D in just one road. So that's where you get your 0 from. And there's 5 down here. I'll just do this one. From D to D, there's 5 different ways. I can either go along this road and then back along that road, that's 1. Along this road and then back along that road, that's 2. I can go along this road and back along this road, that's 3. So that's this one. Or I can go in reverse, so going this way, that's 4. Or I could go up to B and then back to D. So there's 5 different ways of doing that. Anyway, that's a particular context that we've looked at before, that road system way. And it actually comes up a bit in the general math curriculum for year 12. So it'd be interesting to talk to your peers in general maths. But for now, I'm going to show you how to do that multiplication of matrix. Let's look at the procedure. And here it is. So I encourage you now, maybe even to stop the video and just have a read of this. Have a think about what's going on, because it doesn't work quite as you would expect. Okay, well, welcome back. I'm hoping you did pause there and have a look. And so if we do our multiplication, what's actually happening is we create this matrix I've got in the middle here. And we create it by getting the first cell, so cell 1, 1, by doing row 1 multiplied by column 1. So that's A times E, B times G. And the yellow creates that yellow cell. The blue is for cell 1, 2, we do row 1 times column 2. A times F and B times H. The green is for cell 2, 1, and we do row 2 times column 1. There's the 2, 1. CE plus DG, and likewise for pink. So hopefully you can see that pattern there. Hopefully you can also see what I mean by it's a little bit more complex than we'd expect, but also I hope you see what I mean by, but it's actually just basic maths, bit of multiplication, got to add it together, and we have to be just careful. It is highly procedural though. So let's have a look at example 5. Of matrices A, B and C, which two can be multiplied? And let's calculate this product. So what we need to keep in mind here is that when we multiply row 1 by column 1, well, we need to have the same number of cells in row 1 as we have cells in column 1, because we do A times E and B times G. So let's imagine for a second that we're doing, let's say, B times C, which will equal 1, 2, 4, 2, 2, 3 times 1, 2, 1, 2. Okay, so to do the first cell we would do 1 times 1 and 2 times 2 and 4 times what? Now that's actually a dimension mismatch. We can't do this multiplication because there's a mismatch in the number of rows to the number of columns. So B times C doesn't exist. It is not an existent multiplication technique. So what we need to make sure we do is we have the same number here, this is 3, as here. So we have to have the same second dimension for the first matrix as the first dimension for the second matrix. If you draw it out like this, you can see what I'm talking about. So I can tell you the ones that are possible. A times B works because we've got 2 and 2. And I'll keep on changing colours. B times A, well that works because we've got 3 and 3. So that's okay as long as it's B and then times A on the other side. In green, we can't do B times C, we've tried that, but we can do C times B because that's 2 times 2. So C times B works, that has a dimension matching. And we can't do C times A because that would be 2 and 3, but we can do A times C. So we get A times C. So those all work. Now, I've said here calculate this product. I don't want to go through all 4 of those, but let's just do a couple of those. And I'll let you pick now. No, it's a video. I've pre-recorded this, so obviously you can't pick. I'm going to pick instead. Let's do A times B first of all, and then we'll do C times B, and we'll leave it at that. But I'm going to talk about the dimensions that will come out of B times A and A times C. So think about the dimensions that are happening here. So A times B is 2, 3, 3, 2, 2, 3, times by B, which is 1, 2, 4, 2, 2, 3. And the result will be this. Now, I've got my 2 and 2 here. So I've got row 1, row 2, row 3, which means I'll have 3 rows in my result. And I've also got column 1, column 2, column 3. So I'll have 3 columns in my result. So I start by doing 2, 3 times 1, 2. So I get 2 times 1 plus 3 times 2. Now that came from 2 times 1, 3 times 2. And then, and I won't simplify it yet, I'll go through and do each one at a time. So I'm going to run across and do 2, 3 by every single column. So I get 2 times 2 and then 3 times 2. So again this is 2 times 2 and 3 times 2. And my last one, hopefully you can guess, and there should be a plus there, 2 times 4 plus 3 times 3. Now that's my just 2, 3 row. I've got to do the rest now. So I'll do it in silence. I just want you to map along with me. Okay, so that's my matrix, and now I just simplify it and I get my result. So 2 times 1 plus 3 times 2, that's 8. 2 times 2 plus 3 times 2, that's 10. 2 times 4, 3 times 3, that's 17. Then 3 times 1 plus 2 times 2 is 7, 10, 18, 8, 10, 17. And there's my resultant 3 by 3 matrix. Now what's interesting here is this dimension here is 3 and this dimension here is 3. So we've got a 3 by 2 and then a 2 by 3. And these two kind of cancel each other out in a way. The internal dimensions, the inside dimensions in our multiplication, the A32 times B23, the 2's have to match and they cancel each other out, and my result is a 3 by 3 matrix. And that's quite interesting, and it's a very common result you'll see, and we'll talk about it a little bit more in a second. I did promise we would do C times B though, so let's just quickly do this down here. C times B equals, again I encourage you to pause now and see if you can do this calculation, and that is 1122 times by 124223. And see if you get the same as me. And then I'll carry on in silence and you can watch what I've done and see if they match. 3, 4, 7, 6, 8, 14 is my resultant matrix. And interestingly here, my dimensions are 2, 2, and then 2, 3. The internal one's crossed out. I'm left with a 2, 3 matrix, 2 by 3. So you can see it works as we expected. Now I've got a little extension question there which I'll explain briefly. Is matrix multiplication commutative? So commutative is a word that we use to describe if something is commutative, then it means that the multiplication order or the operation order doesn't matter. So for example, let's just go over here and talk about just our general arithmetic. We know that 3 plus 7 is equal to 7 plus 3. So addition as an operation is commutative. 3 minus 7 does not equal 7 minus 3. So therefore subtraction is not commutative. 3 times 7 does equal 7 times 3, and this has to be true of all numbers, but we know it is. So multiplication is commutative. 3 divided by 7 does not equal 7 divided by 3. So division is not commutative in the real numbers and arithmetic we're used to. But in terms of matrix multiplication, is that commutative? Hopefully you recognise now that firstly those two will give us different results, because A times B gives us a 3 by 3, whereas B times A will be 2, 3 times by 3, 2. The 3 dimensions will cancel out, we'll be left with a 2 by 2, which will definitely be a different matrix. So they are not commutative. We also know that C times B is equal to this thing here. B times C is one of the things we said didn't exist. So therefore, matrix multiplication cannot possibly be commutative. Maybe sometimes you'll get that situation where it just happens to be, but it won't often be. Alright, let's have a look at the last thing I want to talk about in this video. That's the rules for multiplication. So for A times B, A must have the same number of columns, that's the second dimension, as B has rows. It's really important. So the second dimension of the first matrix must be matching with the first dimension of the second matrix. A times B and B times A only exist if, and there's two options here, if A and B are matching squares, square matrices, or a little bit more technically, a little bit like the A and B up here. Remember this A and B up here? They weren't square matrices, but they were opposite rectangles. So we had a 3, 2 and then a 2, 3, and that meant that it worked. So we say if A has dimension mn and B has dimension nm. So that must be true, and I don't know a better way of writing that down mathematically without just writing a paragraph, so I'm just going to describe it to you verbally. A squared can only exist if A is a square matrix, because obviously we need the first dimension to match with the second dimension, so it must be the same. And if A is an n by n matrix and B is an n by p matrix, so the n's match, then they will cancel out. The A times B, this should be n then A times B is an M by P matrix. We'll be left with that dimension and that dimension. And so that's a really important thing to recognise as well. Well, that's the end of the video 4, and we're going to run through in video 5 and 6, example 6 and example 7. All the best.